All right, so today we're going to look at sections, combined sections 2, 4, and 3.1, rate of change and the derivative. So we're going to go through the definition of this thing. So the average rate of change versus the instantaneous rate of change. Let's take a look at this real quick. So I drew this little picture for you here. So the average rate of change is basically, we talked about, is the secant slope. This is the slope between these 2 points, P and Q. Okay, so there's the slope of this secant line. It is the change in the y over the change in the x, the average rate of change. And so then we find the values of the function. If this is 1/4 x squared, this is a function name. That's what I drew right here. Then here is P at 1 and 1/4, and Q is at 4, 4. Okay, so then here is the difference quotient right here. And then we plug in our values, and we get a slope of 5, 4. So it's up 5 and over 4. The average rate of change is the slope of the secant line through the endpoints on an interval that is given. So the interval would be 1 to 4. Interval 1 to 4. So this is the average rate of change. This is your secant slope. Okay? And so then let's look at what happens as we shrink the width of this interval. So in other words, what happens if I bring this, instead of 4, what happens if I bring this x value closer and closer to the 1? What if I move Q closer to P? That's what it basically means. Moving Q closer to P. In other words, I want this x, delta x, this change in x, to become 0. I want it to get smaller and smaller. Okay, so I have these drawings over here. That's kind of what's going on. That's what we had before. So here it kind of looks the same, but at this point right here, I'm going to call Q2, and this is going to be at 3, and then this will be 9/4. So here is the secant slope between these 2 points. And we can do the same thing we did up above. We can find the slope of this secant line, so the change in the y values over the change in the x values. And so it'll be y2 minus y1, x2 minus x1. And we can work this out. And in doing so, we'll get this here is going to be a slope of 1. Let's move Q closer, even still. So here, I'm going to move Q to the point 2, 1. So now I have Q getting closer. There's the secant line. You can see that the slope is changing. Okay? It doesn't seem as steep as this one was over here. Let's take a look and see what happens. So again, the change in the y over the change in the x. And then it'd be y2 minus y1, x2 minus x1. And if I work this out, I'm going to get the slope 3/4. So you can see that the slope is getting smaller. So let's move it even closer. So now I'm going to move it even closer. Get it right up into here. Act like I blew this up so we can see it even closer still. And now this Q is going to be at 1.1, and this will be 0.3025. So you see now I'm really close. Okay, so here's that secant slope now. Okay, and so then if I did the change in the y over the change in the x, okay, what am I going to get? Well, I'm going to get 0.3025 minus 0.25 because that's what 1/4 is. And down below, I'm going to get 1.1 minus 1. And if I work this out on a calculator, I'll get this answer right here. Okay, so it's even smaller still. And so the point of this is what's happening is to actually find the instantaneous rate of change, which is the slope of a tangent line at point P. Okay, I can get closer and closer to it, extremely close, and I can get an approximation and an average that's is very, very close to what the actual tangent slope would be. Okay, and so that's what this is referring to. Let me go ahead and show you the note, full form of the notes over here, so you can pause the video and write it down if you want to. But everything I just said right here. So down here, you'll notice that as the delta x gets closer to 0, the slope of the secant line gets closer to the slope of the tangent line at point 1 and 1/4. And the slope of the tangent line at point at a point, in this case, generic point, x equals a, that is the instantaneous rate of change of the function at a. It is also called the derivative of a function at point a. So the slope of a tangent line is the instantaneous rate of change of the function, which is called the derivative of the function. So they're all connected, and you want to make sure you understand that connection. So here you can pause here and draw out these pictures if you wish, and let's continue on. So here is another one, some more definitions and stuff that we want to look at down here at the bottom. Let's take a look at those. Kind of cleans everything up here and gives us the things we're going to be using. This is the same stuff I just showed you up above, it's just now more formalized. So here, the average rate of change of a function over an interval, and this time I gave the interval as a, and then a plus some small number h. So I want these two numbers to be pretty close together. So h is basically just a small number. The slope of the secant line over this interval then would be y2 minus y1 over x2 minus x1. And if I clean this up, I get this expression right here. And this expression is called the difference quotient. Okay, so is this. These are all called the difference quotient. You are familiar with it. It's just basically the slope formula. Here's an alternate form of the same thing. It's just a different look on stuff. Instead of using h, I just used some arbitrary value x I didn't know, and x can be anywhere on the x-axis. But using this notation, I get this difference quotient, which is an alternate form, and you'll need to be familiar with both formats. They mean exactly the same thing. In this case, x is just some number, arbitrarily close to a. Okay, so that would be like the x right there, that a plus h. Okay, so these are the alternate forms, the two forms you want to look at. Make sure that you have those down because they use those quite often. All right, let's turn the page here and see what else we have going on. So here is the instantaneous rate of change top. So let's go ahead and look at that. The instantaneous rate of change of a function at point A is the slope of the tangent line to the graph at x equals a. It is also called the derivative of the function at x equals a. And so here's our formal limit definition of a derivative. This little symbol right here, f prime of a, means the derivative of the function f at a. This is the derivative of the function f at a. And it is defined as the limit as h goes to 0, because I want that little h to be really, really small. Let's take a look again at our picture. I want h to be a really small number, so as it goes to 0, this point is getting closer and closer to this point, making that point come closer and closer to this point. Okay? So as h gets closer to 0 of this quantity, the difference quotient. So this is the slope of the secant, and we're making the slope of the secant have that second point get really, really close to the first point. So it becomes the slope of a tangent. So this limit is the slope of the tangent. And this is the same thing using the alternate form of the difference quotient. So this is what the derivative is. It is the derivative of a function at a is these limits, provided the limit exists. So if the limit doesn't exist there, then there's no derivative there. And we'll talk more about that as we move along. All right, so here is some other things. This is a keynote. Okay, a lot of times they will talk about all these things interchangeably, so you need to be familiar that when they talk about any one of these things, they're talking about all of these things. For the derivative of a function at a point A, the following are equivalent. The derivative of a function at A, that's what this means. When you see that symbol, it is the derivative of a function f at A. This symbol right here means that this is the instantaneous rate of change of the function f at a. The same symbol is the slope of the tangent line to the graph of the function at a. And this symbol right here, the notation is the slope of the function curve at A. So they'll say, what's the slope of the curve at A? They mean the same thing. It's the derivative. And it's because at that one particular point, there is a tangent line there. So that means that that point is on the tangent line. That point on the curve must also have the same slope as the tangent line slope. That's what they mean by that. Okay? So you want to be familiar with all these different looks of the same thing. Okay? So now we're going to look at the derivative as a function derived from f by considering the limit at each point of the domain of f. So here's a definition. Okay? This is a derivative of a function f. So now, notice that it's not at a point. This is the actual derivative itself. It is a function in and of itself. See? This is the derivative of the function f, whose variable is x. Okay? The derivative of a function f with respect to the variable x is a function f prime, whose value at x is given by this notation. And you'll notice it's the exact same notation with a slight variation because there's no a. It's an x. So wherever there was an a, there's now an x. And when you get done, it's going to produce a function with the variable x. When I did this up here with the letter a, this will always produce a number, which is the actual slope. This will give me a function that will allow me to find the slope on the curve at any point with just that function. And so you'll notice that it's the same limit definition as before, like I said, very similar. Okay. And so, provided that the limit exists. And so you look at my note here, it says the derivative of the function will allow us to find the slope of the curve at any point in its domain. So I don't have to keep going back and doing this at every point I'm interested in. I can just find this function and then plug in every point that I want. Okay. Let me move this just a bit so we can read it. Okay. The domain of f prime is the set of points in the domain of the function for which the limit exists. It may be smaller than the domain of f because there may be points where this limit up here will not exist. If f prime of x exists, we say that f has a derivative, that it is differentiable at x. A function that is differentiable at every point of its domain is a differentiable function. So this is a lot of notation or definitions here that they're going to use in questions, but you want to make sure you understand what they mean. So when they say a function is a differentiable function, that basically means that I can take the derivative at every point in its domain. Okay? Here are some of the notations that can be used to express derivative. These are not all of them by any means. They are just a few, the most common ones. You have the f prime of x. Sometimes we have y equals equations, so you can say y prime. You can say the dy over dx. This means the derivative of y with respect to x. And then the last one over here is the derivative of a function with respect to x. Okay? Again, this is just a few of the notations that you're going to be seeing. And so when you see those, just know that they all mean the derivative. So now I have an example I want to look at. I'm going to walk you through everything together here. All right, so here's the story. So the altitude of a helicopter A is given by A of t. Selected values of A of t are given in this table. The altitude of helicopter B is given by this equation. And t is between 0 and 20. Both A of t and B of t are measured in feet, and time is measured in minutes after takeoff. So with that information right there, let's answer some questions. So what is the average rate of change of A of t over this time interval from 0 to 20? Indicate units of measure. So one of the things that's very important in your calculus tests and stuff like that is to make sure you indicate units of measure when they tell you to, because that means you're going to get points associated with it. So an average rate of change, we know, start thinking about it. Average rate of change means it is the slope of a secant line, which means I need to use the change in the y values over the change in the x values, in this case, the change in this over the change in that. And so my average rate of change, when you write and display your work, you need to show what you mean. Don't just get a number. They are looking that you are expressing things properly and so they can give you the points that you need. This is the change in the height. I'm not using a y because I don't have a y value. I could have used A of t. And this is the change in the time. So what is the change in the height between 0 and 20? Well, it is, now this is the part that you want to write. It's the difference quotient. Don't plug in the numbers yet. Plug in what you mean. It means I'm going to do A at 20 minus A at 0 over 20 minus 0. Write that first. Then plug into that. Now I can plug in the values that they represent. And this is 20 minus, I think I made a little typo on my own self. For some reason I have a 5 down here, but we'll put 0. So my numbers here will be suspect. Okay. So know that I have an error in my notes that I'm going to be dealing with here in just a moment. And then just turn my calculator off. Anyway, so this is going to be what? 1,500 or 15,000 over 20. And then we can work this out and get a value. But whatever this value is going to be in what? What is the change in the y values? They are in feet, and the time is in minutes. So this is feet per minute. Okay, and we can reduce that out and get a value for right now. But also on the AP exam, since this is a free response question, you can actually stop right there. Okay, let's go ahead and look at the next one. What is the average rate of change of B of t over that interval? Okay, indicate units of measure. So what am I going to do? Same thing. What is my average rate of change? It is the change in the height or the change in the time. It is B at 20 minus B at 0 over 20 minus 0. Okay? And then we come down here and we can work this out. So what is B at 20? Well, we have an equation for that. So I can type in and plug in, here's the 20. This will be a negative 11 times 20 squared plus 900 times 20 minus, and then 0 plugged into all of that. So that's just going to be 0. And then this is going to be 20 minus 0. And I can work this out and get an answer. Again, my calculator turned off here, so. See if I get it going real quick. And so I can type this in right here, get a value. So I got a negative 11 times 20 squared plus 900 times 20. And I'm going to get 13600 divided by 20. And I have 680, and again, feet per minute. Okay? And so this is what you would show me and what you do on your tests. Okay? So again, make sure you put in the proper units at the end of this thing. Because they are a rate. Remember, rates have to have units in this fashion. So the last one here is, what is the instantaneous rate of change for B of t at that? T equals 7. Okay? So the instantaneous rate of change, remember, has those formulas we had. Let me show them to you again. I'm going to use because it's at a value, I'm going to use one of these two. I'm going to use this one right here. Okay. And so I'm going to come over here and I'm going to do that. And so technically I can write it as B prime at 7. And then I'm going to plug in what this equals to based off of that definition is the limit as h goes to 0 of b of 7 plus h minus b of 7 over h. And our job now is to work this out using our formula for b. And I'm going to get the limit as h goes to 0. And then I got to plug in this quantity in for that t. And when you do that, I recommend that you do it just like this. Type it in. Don't try and work it out at the same time. There's too much going on. Notice I'm putting the first term, this b of 7 plus h, in print big brackets like this, because I want to make sure I separate it from this side over here. Now I need to plug in 7 into that equation. And then 900 times 7. Close the bracket there, all over h. So our goal here is to expand all of this out, combine all like terms into one big expression, okay? And so let's do that. So this is now the limit as h goes to 0. And I'm just going to write all that out for you so you can see the expansion. You can double check all my work to make sure I do it right. This is what I have. 6,300 plus 900 h. And then the back side, if I take that and work that out, I should get the number 5761. That's all over h. And then if I start looking at this and combining like terms and bringing everything together, I now have this limit. And I should have a negative 11 h squared plus 746 h over h. And you will notice that there is a common factor on top of h. And that's what you're hoping for, okay? Because this h on the bottom is going to be a problem. If you think back to our limits, h goes to 0, then that's going to be a 0 on the bottom, and I have an issue here. So, but if I factor out that h on top, you'll notice that it's going to reduce. So I take out an h on the top, I have a negative 11h plus 746. There's the h on the bottom, and those reduce out, leaving a limit that I can figure out fairly easily. So as h goes to 0, this quantity right here will go to 0, leaving me the answer 746. And that will be in feet per minute. And that is the instantaneous rate of change of B at 7. Okay, so that's how that works. All right. Now, in the notes themselves, so I'm going to pause it right here, let you copy this one down. You can, again, do a calculator and figure out what this value is on your own. But let you copy the work down. So just pause and copy that. And pause and copy that if you need to. Because I do have an error in my master notes that I have to fix. All right, so let's look at another example that I have down here. Okay, in this case, we're going to find the derivative of f of x, which is x squared plus 4x. We're going to find the derivative of this. We're going to use that derivative to find the instantaneous rate of change of the function at these values. So instead of doing 5 different little ones we just did, instead of doing 5 of these to get a value, I'm going to find the derivative generically as a function and then plug these values into it. So here's how this works if you want to follow. So what is f prime of x? Well, by definition, I can use that right here. Okay, it's that limit. So I'm going to come over here and I'm going to take that and I'm going to use this limit. So h is going to go to 0. And we're going to have f of x plus h minus f of x over h. And we're going to do exactly the same thing we did in the other one. We're going to plug these quantities into this equation. So this is the limit as h goes to 0 of, so x plus h into this formula becomes x plus h squared minus 4 times x plus h minus f of x. Well, f of x is right there, so that is x squared minus 4x. Again, notice I put brackets in the minus sign between. I want to make sure I don't mess up. Okay. So the next thing I do is I'm going to expand all this out. I'm going to, and then clean it all up. Here it is expanded, so you can double check my work though, make sure I did not make an error. And you should get something like this. So you get x squared plus 2xh, and then minus 4x minus 4h. And then over here is going to be the same thing, x squared minus 4x all over h. And then clean this up, combining like terms, and you're going to get down to that smaller expression, hopefully. And you get 2xh plus h squared minus 4h over h. And you'll notice that the top has the common factor h. So by factoring that out and simplifying it out, I'm going to do that. This becomes h minus this, and then I end up with 2x plus h minus 4. And as h goes to 0, this gives me the expression. So f prime of x is this expression 2x minus 4. That is the derivative function. Once I have that, then I can just simply plug in these values. So what is f prime at 0? Well, it is 2 times 0 minus 4, or negative 4. What is f prime at 1? Minus 4. Okay. And then what is f prime at 2? What is f prime at 3? And what is f prime at 4? And so you can plug all these values in and work all these values out. Okay. This will be 2 times 3 minus 4, which is 2. And then this is 2 times 2 minus 4, which is 0. So there's all those. Let's see how much quicker it was once I had the original function, the derivative function. It's very simple to find the derivative at any one of those particular points. If you did this for each one of those values, you will get the exact same numbers that I got right here. So this is much quicker for all those assignments. I have another example here. Just change the function for you so you can kind of see how to do different looks, different functions that when you do your work later on might be more easy to do. Okay, so we're going to do the same thing. We're going to find the instantaneous rate of change of f of x, which basically means I want to find f prime. So what is f prime of x? And so we know it's the limit as h goes to 0 of f of x plus h minus f of x over h. So let's plug in our values using this function right here. So this is going to be, even though I don't need them, I do recommend highly that you keep using them. The brackets is what I'm referring to. Because these are square roots, they're already separated. But if you're consistent, then you can just, you don't make mistakes in that fashion. Okay? So this is what I have right now. Okay? There is a common factor up above already. I don't know if you noticed it or not, but this expression on top and this one right here both have the square root of 3 involved. If you think back to our limits rules, because that is a common factor and it's a constant, I can take it all the way out to the front as the square root of 3 times this limit. It's just convenient. You can carry it through, but it's a little bit more challenging to do that. It's better to get it out. But if you don't notice it, you can still continue on with it in there. Okay? Now, at this point, there's nothing I can really do here because I'm going to get an indeterminate form 0 over 0 here. I can't plug in 0. So I have to use one of our techniques, which was the rationalization technique. So remember that rationalization technique is to multiply the top and bottom by the conjugate of that. We're rationalizing the numerator here, so this expression becomes the square root of 3 times that whole thing. And you'll have x plus h minus this over h, and we're going to times it by the conjugate plus the square root of x plus h plus the square root of x. So this quantity to that quantity to that, and you end up with this right here. The bottom, you're not going to do anything. You're just going to leave it plus h. And the top is just the product, like the difference of two squares. So if I multiply these two quantities together, I'm going to get simply x plus h, and then minus this quantity squared, which is simply x. And you'll notice on top, the whole thing simplifies down to become h on top. X's drop out, you're left with an h. There's the h on the bottom. And so you have this expression right here. So the h is reduced out. Okay? And you're left with, as you clean everything up, these drop out, plug in the 0, I get a square root of x plus the square root of that's 2 square root of x's. So let me just go ahead and do that so you can see it. This becomes the limit as h approaches 0. It's going to be 1 over this expression. And so then I can say that f prime of x is equal to the square root of 3 over 2 of those. So that right there is my derivative. And then I can plug in these 3 values in here and get an answer. So what is f prime at 0? It's the square root of 3 over 2 times the square root of 0. And that is undefined because you cannot have 0 on the bottom. Okay? And then I can have f prime at 3 over 2 to the square root of 3, which is 1/2. And then I can do f prime at 12. And then this cleans up using your rules and your simplifications, and you'll get 1/4. Okay? So there's those right there for you and how to write it all out. I'll pause it right there, and you can stop it and write it all out if you need to. And then we have a couple more things to look at. Let's go ahead and take a look. Bring this in again. All right. Note, 0 is in the denominator of f of x, but not in the domain of f prime of x. When this happens, we say that f of x is not differentiable at x equals 0. From the graph of the function, the square root of 3x, okay, what happened there? Since the derivative is representing the tangent lines to a curve, what does the tangent line at 0 look like? Well, as I get closer and closer to 0, the tangent line is turning vertical. And vertical lines have no slope. That's why it's undefined. Okay? So that's what happened in that derivative realm. The point exists in the function, right? I plug in 0, I'm going to get 0. There's a point there. But the derivative, the nature of it is the slope of a tangent line. And the tangent line at 0 is a vertical line, which means it has no slope. And that's why we got the undefined. Okay? So the last one here is just another thing we need to be able to do to ask a lot of questions on this. And that is, how do I find the equation of a tangent line to a curve? So in other words, we can find these slopes, right? The derivative is the slope. This is the slope of the tangent line at 3. That's what this means. So what is the tangent line equation? So This is just a change of what you learned back in Algebra 1, actually. What do you need to write the equation of a line? Well, you need a point and a slope, and you need the point-slope formula. This is what you did back in Algebra 1. But what does this look like in calculus now? Well, the slope is the derivative at a point, which is this limit. The point is any point that I want, and usually what we do is we use the point A, since we're going to be the tangent line at A, and then the value of the function at A, f of A. So there's my point. So this equation right here becomes this equation right here. And a lot of times they'll move this f of A over here. So it'll be, a different format would be y equals f of A, and then f prime of A, x minus A. So this is the same thing. They usually just move that over. But I wanted to show you that that's what it is. Okay? So pause it right there. Write that down. That's very important. You're going to use that quite often throughout this course. All right? So we have one more example, which is where we're going to find the equation of a tangent line. So find the equation of the line tangent to a function f of x equals 5 over x minus 1 at x equals 4. Okay? So to do that, we need to find a point and a slope. Okay? So let's start with the slope. What is f prime at 4? So based off of that, we can use our definition. I'm going to use the other one this time. I'm going to use this one. Why? No particular reason. I just want to show you how it's used. Okay? So I'm going to use this one to find the slope at 4. So this becomes the limit as x approaches 4 of f of x minus f of 4 over x minus 4. So now we go through here and we work this out. F of x is 5 over x minus 1. F of 4 is 5 over 3. And then x minus 4. So now it's about cleaning up the top. Okay, if you remember back in our pre-calc in Algebra 2 days, we need to find the LCD, which is 3 times this, multiply the top and bottom by it to get rid of the fractions on top. And the LCD on this case is going to be 3x minus 1. So we're going to multiply the top and the bottom by that. So the top up here becomes 5 times 3 minus 5 times x minus 1. And the bottom becomes the product of these two things right here, which is 3 times x minus 1, x minus 4. Okay? So now we need to clean all that up. And I'll give you the limit as x approaches 4. And then the top should be negative 5x plus 20. And the bottom just stays the same. Don't try and multiply that out. Oops. This is x minus 4. Okay. Then we notice, okay, well, look, I can factor the top, and you'll notice you should always be looking for that kind of thing to make it easier, because if I plug in 4, this is going to be a 0 on the bottom, and I can't have 0 on the bottom, so that x minus 4 has to go away some way, which means the top probably can factor. So if I factor out a negative 5, I'm going to get x minus 4. Okay, so that's kind of a clue that if you can't plug a number in, look and see if you can factor some things, use a different technique that's available. We can see that these are going to reduce out, and this limit becomes this. Negative 5 over 3 times x minus 1. Now I can use direct substitution, plug in our numbers, and get a negative 5/9. So there is my slope right there. So remember, I need a slope and a point. Since this is the slope, I need the point. I need the point at x equals 4. So what is f of 4? That is 5 over 4 minus 1. And we already found this value anyway, and that is 5/3 because we found it right there, remember? Okay, so there's my point, there's my slope, and so we can go right to our equation. It is y minus the point value, the slope, times x minus 4, and that is the equation of a tangent line. And again, if you wanted to, you can move the 5/3 over, and that's the same thing. Okay, but the AP exam will take either one in a free response setting. If it's multiple choice, most likely you got to match it to this thing down here. They might even expanded this thing out, combine like terms, all that stuff. But this is how you can view it in the free response. So that's 2, 4, and 3, 1. We're going to do a lot of practice on that one, and because it carries all the way through up into the AP exam. So that ends this video, and we'll do more in class.